The deeper we stare into space, the stranger it becomes. For all the charts, models, and simulations we've built, the universe still throws curveballs. Anomalies so bizarre they make scientists question the rules of physics themselves. From signals with no source to gravitational ripples without collisions. NASA and global space agencies have uncovered a catalog of cosmic mysteries that simply don't add up. The radio signal from beyond the Milky Way started out as a whisper. Just a small burst of energy hidden in years of data from radio telescopes. They almost missed it, the astronomers. It looked like a bug at first, but then there was another, one more. Each signal came from a direction far beyond the Milky Way and was milliseconds fast and very strong. FRBs stand for fast radio bursts. Even though we've found hundreds so far, FRB 121102 was the first one that was proven to repeat, which caused a lot of excitement in the scientific community. The signal wasn't just odd. It came from a 3 billion light-year distance dwarf galaxy that is very old. No one could say why. A typical FRB lasts just a few thousandths of a second. But in that tiny moment, it can release more energy than our sun produces in an entire day. That's the cosmic equivalent of hearing a match strike and realizing it lit up an entire city block. When FRB 121102 repeated, meaning it wasn't a one-time cosmic explosion. It overturned everything scientists assumed about these phenomena. This wasn't a dying star's final flare. Something was producing it repeatedly, reliably, intentionally. No one knew where the signal came from. A very small and faint galaxy that looked like a dried-out spark next to the Milky Way. That fact made the mystery even stronger. Why would something so bright and full of life come from a place where there isn't much going on? Scientists thought that these kinds of loud signs would come from the busy, dense centers of galaxies, or from black holes in galaxies that are colliding. But FRB 21102 came out of a pretty quiet part of the universe, like thunder in a field that was empty. Then came the polarization, a twist in the signal's wave pattern. This meant the burst was traveling through an incredibly strong magnetic field. One far stronger than anything expected in that region of space. It suggested the FRB might be near a neutron star, or possibly a magnetar, an ultramagnetic corpse of a star. But even that didn't explain the power or the repeating pattern or the pinpoint location, which seemed embedded in something scientists couldn't clearly resolve. NASA joined the fun. This was also true for radio systems around the world, like Arecibo, Chime, Greenbank, and VLA. The Very Large Array in New Mexico made an amazing map of the bursts and tracked them to a part of the dwarf galaxy where stars are being formed. But that made us wonder even more. Was this thing a neutron star inside a dense nebula? Did the young magnetar send energy out into space as it spun quickly? If that's the case, why did it produce so much more energy than what is possible theoretically? Some signals showed intervals that resembled a heartbeat, pulsing every 57 days with short periods of frenzied activity followed by silence. And that pattern didn't just repeat, it persisted for years. This wasn't random, it wasn't noisy, it was a clock. Something far away was ticking in perfect rhythm, and nothing we knew could explain how or why. A lot of theories came in. Some people mentioned a binary system with a magnetar going around a huge black hole and only exploding when it passed through certain patterns. Others suggested a new type of star object that we hadn't seen before. Something in between a neutron star and a quasar. Strangest ideas, though, got the most attention. Could it be man-made? Were FRBs being used by some kind of alien mind to send messages across galaxy? No official institution claimed that publicly, but many researchers admitted privately that the precision and energy of the bursts were puzzling, uncanny, even unsettling. It wasn't just the power. It was the intent. These weren't like the one-off explosions of dying stars. They repeated. They pulsed. They were consistent. And then came something even stranger. Other repeating FRBs were found. FRB 01800916 showed a 16-day cycle. And unlike 12102, it came from a spiral galaxy much closer to Earth. Now, the question was bigger. Are all these bursts the result of the same mechanism? Or are we looking at a family of cosmic phenomena we barely understand? NASA launched follow-up investigations using both space and ground-based telescopes, hoping to triangulate signals across multiple wavelengths. Radio, X-ray, infrared. But so far, no accompanying light, no visual fireworks has ever been directly linked to these bursts. They arrive, blast our detectors, and vanish. The deeper question is this. If energy this powerful can reach us from galaxies 3 billion light-years away, what else could be out there hiding in frequencies we haven't even begun to monitor? The FRB story has taught scientists one humbling truth. Space is a noisy place, and most of that noise is still undeciphered. There is still talk from FRB 102 right now. There are more and more signs, and they still can't be explained. Stars have been ruled out. Comets have been ruled out. They have ruled out getting involved. Whatever it is, it's real. It keeps happening, and it's not from here. Voyager 1 sent back data that defied physics. This wasn't what Voyager 1 was meant to do. Over 15 billion miles away from Earth, it had already gone beyond all expectations after almost 50 years of travel. Voyager 1, which was launched in 1977, was the first spacecraft sent by humans into space between the stars. It flew by Jupiter and then Saturn, finding new moons and taking pictures that will blow your mind. In the end, it went past the heliopause, which is the unseen line where the sun's impact ends and deep space begins. Then in 2022, it sent back something strange. The data coming from Voyager 1's attitude, articulation, and control system, AACS, didn't make sense. This is the system that tells the spacecraft how to orient itself, where to point its antenna, and how to stay aligned. It's like the gyroscope in your phone, but far more precise and infinitely more vital in the vacuum of space. Without it, Voyager 1 can't keep its high-gain antenna aimed at Earth, and for some reason, it started transmitting nonsense. The telemetry data showed the AACS was functioning. It was keeping the antenna pointed correctly, but the information it was sending about its own status, temperature, voltage, and direction was completely incoherent. The readings made no logical sense, as if Voyager's mind had split from its body. Even stranger, no onboard fault was detected. The spacecraft wasn't in safe mode. Its signal remained strong, but what it was saying didn't match what it was doing. Think about that. You're driving a car. It's moving just fine, staying in its lane. But when you check the dashboard, the speedometer says you're going 900 miles per hour. The fuel gauge spins in a circle. The GPS insists you're underwater, but you're still cruising down the freeway. That's the situation NASA found itself in. And the deeper they dug, the more puzzling it became. Was it a software glitch? Maybe radiation scrambled Voyager's ancient memory? Could cosmic rays, high-energy particles flying through space, have flipped a bit or corrupted a subsystem? These ideas were floated, but there was no evidence of hardware failure, and rebooting the system remotely is risky. If you send the wrong command, Voyager 1 could stop talking to Earth forever. NASA's team began troubleshooting slowly, carefully. Remember, Voyager 1 is so far away that it takes nearly 45 hours to send a signal and get one back, 22.5 hours each way. Imagine debugging a computer that responds once a day. That's the reality of deep space engineering. You don't get second chances. Then came the most baffling theory of all. What if the spacecraft was sending telemetry from a different part of its system, one it wasn't even supposed to use? That would mean it had silently rerouted its own data through another channel, something never programmed into its software. In other words, Voyager 1 might have improvised. Let's pause there. This is a spacecraft launched during the Carter administration. Its computing power is less than a digital wristwatch. Its memory is measured in kilobytes. It was built before the internet, and yet it may have figured out how to keep communicating by using parts of itself in ways no engineer intended. That's not just impressive, it's borderline eerie. Eventually, months later, NASA announced that Voyager 1 was indeed routing data through an old defunct computer, one not used in decades. The spacecraft had apparently begun using this outdated system without informing Earth. No one knows exactly why. The team suspects it was the result of a chain reaction inside the AACS, possibly triggered by a single flipped bit or hardware degradation after decades in deep space. But even that's just speculation. This is where the science rules become less clear. As of now, Voyager 1 is no longer affected by the sun. It's working in interstellar space, which is colder, darker, and farther away from other places we've sent robots. The particles, radiation, and forces outside of our solar system don't act the same way they do inside. There might be new kinds of disruptions happening because of these situations. Or are we finally hitting the end of what our technology can do in space? Some scientists even floated speculative ideas: quantum interference, exotic particles, or unknown forces interacting with Voyager's systems. While those remain on the fringe, what's undeniable is that Voyager 1 did something no one programmed it to do. And it managed to stay alive and talking the whole time. Eventually, engineers reconfigured the spacecraft to resume proper telemetry by instructing it to use the working system again. But the incident is now legendary among mission controllers. It's a moment where the universe reminded us, even when you build something to be predictable, space has its own plan. Voyager 1 continues to travel outward, inching deeper into the unknown. Now, in its 47th year of operation, it still whispers to us across a vast gulf of time and distance. And sometimes, what it says doesn't just challenge engineering. It challenges what we think machines can do. The unmapped object near the edge of the heliosphere. They don't mean a sharp wall or a bright line when they talk about the edge of the solar system. The heliosphere is what they mean. It is a huge bubble made of solar wind and magnetic fields that the sun inflates and stretches billions of miles in all directions. It keeps us safe from cosmic radiation and separates our space from the space between the stars. Spacecraft like Voyager 1 and Voyager 2 have been slowly moving toward and now through that line for decades. On the other hand, in 2018, their sensors picked up a signal from an object that didn't fit. Both Voyagers carry low-energy charged particle LECP detectors, tools designed to sense changes in the energetic particles that fill the heliosphere. As they neared the heliopause, the final boundary before interstellar space, they began reporting strange fluctuations, not just in radiation but in the direction and density of incoming particles. These changes suggested the presence of a solid or semi-solid body near the outer edge of our solar system, one that had never been mapped, observed, or predicted. The region in question lies between 2130 astronomical units from the Sun. That's 11 to 12 billion miles away, far beyond Pluto. In this zone, space should be relatively uniform. Voyager 2, which entered interstellar space in 2018, was expected to record a smooth transition as it pierced the heliopause. But instead, its sensors detected a localized distortion, as if a large object was bending the magnetic field around it. The thing didn't give off any light. Infrared or visual devices couldn't see it. Its magnetic and gravity pull were clear, though. It's like driving on a smooth road and all of a sudden hitting a patch of rough terrain. There are no cracks in sight, but your car shakes like a huge object just went by nearby. This led some researchers to propose the existence of a hidden planetary mass object, possibly a rogue planet or large icy body hovering near the heliopause. The idea isn't new. Planet 9, a hypothesized Neptune-sized object in the outer solar system, was proposed based on similar gravitational effects. But this new anomaly was in a different place, and moving in an unexpected trajectory. Worse, it didn't match any known orbit. It wasn't circling the sun in a way typical of distant Kuiper belt objects or scattered disk bodies. It seemed to drift like a foreign object just passing through, not captured, not bound, and not behaving. When NASA and JPL tried to model the Voyager data, the numbers kept spitting out something uncanny. The source of the distortion was massive, but not dense. Not a black hole, not a star, not even a moon. More like a cloud-wrapped object, possibly coated in reflective ice or made of exotic matter. Something unlike anything else in the known system. Space telescopes like WISE and Spitzer were checked for any thermal signatures in that region. Nothing. It was like trying to photograph a shadow that wasn't casting any. And yet, the magnetic field distortions didn't go away. They lingered, and they moved. Could this be a frozen interstellar object like Oumuamua? But far larger? Maybe. Oumuamua shocked astronomers in 2017 by being the first confirmed object to enter our system from another star. But this new anomaly wasn't zipping past. It was lingering at the edge, almost waiting. The conspiracy theories arrived quickly. Was this a probe, a concealed ship, a cloaked satellite? Scientists, of course, dismiss these claims, but what they can't dismiss is the data. The field lines bent. The particle flow changed. Something is there. It's not the only one. Later, Ibex, the interstellar boundary explorer, a spaceship watching the edges of the heliosphere from Earth's orbit, found blips that were the same as those seen by Voyager 2. Ibex confirmed that strange releases, known as ENA flows, energetic neutral atoms, were coming from the same area. This added weight to the idea that a large object, maybe hundreds of kilometers wide, is interacting with the heliosphere at its weakest point. Some even suggest it could be the outermost member of our solar system. A planet-sized ice body that formed alongside Neptune and was ejected outward long ago, now circling at the very edge in a ghost orbit we never thought to check. Or it could be something alien to our system entirely, not part of our formation history, not even gravitationally bound to our sun. The Interstellar Mapping and Acceleration Probe, IMAP, which is about to take off, could give us the best chance of getting a better view. It has tools that are meant to find and fix ENA problems with a lot more accuracy than Ibex. Until then, the edge of the solar system will stay a border full of plasma streams, magnetic walls that move, and now the possibility of a visitor we did not expect. Dark matter disruption detected in an empty zone. There are places so empty in the vastness of space between galaxies that they are known as cosmic gaps. These are huge areas of space with almost no matter, no stars, and no structure that can be seen. Things should go smoothly in these places. No light, no motion, and no excitement. Not so in 2020, when a NASA-funded group of scientists looked at gravitational lensing patterns in a known void. They saw something that didn't make sense. The gravitational field of an area with no obvious mass suddenly became distorted. It started with data from the Hubble Space Telescope and the Dark Energy Survey. Researchers were mapping how light from distant galaxies bent and stretched as it passed through foreground space, a method called weak gravitational lensing. This process allows astronomers to detect invisible mass like dark matter by the way it warps space itself. Typically, these distortions follow predictable patterns. But in one region, an allegedly empty area between two galaxy clusters, the lensing map showed a sharp localized warp that appeared and disappeared over several months. It does not make sense. Dark matter doesn't give off reflect, or take in light by definition, but it does have mass, and that mass should stay the same. It doesn't get worse. It doesn't beat. It doesn't move all of a sudden. Still, the data showed a changing lensing signature, as if a huge unknown object had moved across the field of view and then disappeared. Astronomers ran the models again. Same result. The light from galaxies behind the void had briefly bent as if tugged by an invisible hand. When checked against known catalogs, there were no galaxies, no black holes, no gas clouds, no rogue stars, nothing that could explain the shift. It was as if a chunk of gravitational influence had passed by, completely dark. Some speculated it could be a dark matter clump, a dense cluster of the invisible stuff passing through space. But dark matter, based on all previous data, doesn't usually form in such isolated pockets. It tends to surround galaxies or filaments in the cosmic web, not wander through voids on its own. Another scarier idea was that this could be a dark matter wave, which is a ripple in the universe's structure of unseen mass, caused by something we haven't found yet. If this is true, it means that dark matter isn't fixed and can move through space in concentrated ways, like wind gusts in a storm that we can't see. That's really scary, because it means that the rules we use to understand mass, motion, and how gravity works might not be full. NASA's Nancy Grace Roman Space Telescope, due to launch soon, is designed in part to explore exactly this kind of phenomenon. With more sensitive instruments and better wide-field resolution than Hubble, it may help pinpoint these shifting gravitational ghosts. But for now, all we have is a single piece of hard evidence: gravity-bent light in a place where nothing visible should have been able to do that. Some fringe physicists even posited the idea of a dark matter solitonic particle wave structure that moves through space like a self-contained ripple, distorting space-time as it travels. If that's true, we might not be dealing with matter at all, but with a moving fluctuation in gravity itself, a distortion created by the universe's unseen scaffolding. Could we have seen something really strange go by? Like a primordial black hole or a piece of physics from before the Big Bang? We missed something so small and dark that not even our best tools could see it, but with enough mass to bend space-time as it went by. The findings are now part of the science record. No matter what, a moving ghost mass went through an empty area. What it left behind was a scar in the shape of bent stars. It didn't leave behind any light, radiation, or residue. If this is just one change caused by dark matter, how many more are going on right now in places we can't see? What number of gravity distortions do we not see because our cameras have blind spots? What does it mean if the world changes and moves around more than we thought? At this point, experts can only watch, drawing, waiting. We're on the verge of a new type of physics that doesn't even have rules we know about yet. If dark matter can move and move in ways that make it look like mass without having any shape. Pioneer anomaly, the spacecraft that slowed without reason. NASA sent Pioneer 10 and 11 into space in the early 1970s with two goals in mind: to explore the outer planets and then glide into space between the stars. They mostly did what they said they would do. In 1973, Pioneer 10 flew by Jupiter. The next mission, Pioneer 11, flew by Saturn in 1979. After their tasks on planets, both ships kept going out into space, being quiet, dependable, and loyal. For a while they were. By the 1980s, mission engineers began noticing something strange. Both Pioneer 10 and 11 were slowing down, just slightly as they left the solar system. It wasn't dramatic. It wasn't a crash or a failure. It was subtle. About 8.74 attenuan a number so small it might seem meaningless. But in the precise world of celestial mechanics, that number was a scream. You see, deep space navigation is ruled by Newton's laws. A spacecraft once launched and left alone should continue on its path at a steady speed unless acted upon. Every movement, every acceleration, every deceleration, it all has to be accounted for. And with Pioneer, something didn't add up. There was no known source for the deceleration. It was like space itself was holding them back. Scientists double-checked everything. Could it be solar radiation pressure? No. The effect was too persistent, and it continued long after the sun's influence had faded. Was it gas leaking from the spacecraft? That would have shown up in attitude data, and there were no signs. Could the onboard radio systems be pushing them back? Unlikely, and the calculations didn't support it. Still, the strange thing kept happening. For many years, scientists were pretty scared when they heard about what they called the Pioneer anomaly. Because if something as simple as Newtonian motion wasn't working the way we thought it would, then either our models were wrong or the ship was being affected by something new. Theories piled up. Some thought it was a thermal recoil force, essentially heat emitted from the craft's power systems, causing a tiny push in the opposite direction. Others proposed more exotic ideas, modified gravity theories like modified Newtonian dynamics, or even an interaction with dark matter or unknown space-time properties in the outer solar system. One group suggested the crafts were entering a region of altered space-time, where time and gravity behave differently. Another proposed the possibility of an undetected planetary mass, something like a hidden dwarf planet tugging subtly on the spacecraft. But those ideas lacked evidence, and still, the anomaly remained. In 2012, a partial explanation emerged. A detailed thermal analysis showed that some of the deceleration could indeed be caused by uneven heat radiation from the spacecraft's radioisotope thermoelectric generators. Essentially, heat from the onboard systems was bouncing off parts of the spacecraft and creating a faint but constant backward push. It made sense. It accounted for some of the anomaly. Even today, there remains a discrepancy, small but persistent, between the modeled forces and the observed motion of the Pioneer spacecraft. In the vacuum of space, where everything should behave like clockwork, Pioneer 10 and 11 still tell us a different story, one of resistance, one of subtle warping. No other spacecraft has replicated the anomaly quite like Pioneer. Not Voyager, not Cassini, not New Horizons. Some say it's because those missions had different configurations or flight paths. Others wonder if something unique about the Pioneer twins, their shape, their materials, their spin stabilization, interacted with space in a way we didn't anticipate. Maybe they just happened to walk by something that the other people didn't see. The Pioneer anomaly is still one of the most interesting riddles in space travel that hasn't been solved. It is where engineering, physics, and astronomy all meet. Any machine, no matter how well it behaves, can run into the unknown. And in the silence of deep space, even the faintest sound of resistance can be heard like thunder. Pioneer 10 and 11 are no longer making noise. It's been years since their last broadcast. Infrared blips from a supposedly dead star field. There are empty spots in the sky at night. It's not that there's nothing there, it's just that what was once bright has gone out. Astronomers call these places dead star fields. They are places where supernovae have already happened. Stellar fuel has been used up, and what's left are white dwarfs, neutron stars, or cold debris from the stars. Most of the time, these areas are quiet across the board. But in 2019, a scan of the very far sky saw something flashing in infrared light where it shouldn't have been. The data came from the WISE telescope, NASA's Wide Field Infrared Survey Explorer. WISE is designed to spot heat even from incredibly faint or distant objects. When scanning a known cold region, previously catalogued as devoid of active stellar activity, WISE detected 3 distinct infrared flashes spaced irregularly over a span of 36 days. Each flash lasted just hours, then disappeared. This wasn't just a sensor glitch. Multiple instruments confirmed the readings. Follow-up observations with the Spitzer Space Telescope and ground-based arrays showed residual warmth in the area, but no central source. There was no star, no brown dwarf, no protoplanetary disk, just faint ripples of infrared light, as though something invisible had flared up, then cooled just as fast. What could make a place hot when it shouldn't be? The first idea was that micrometeoroids were falling into each other and releasing heat energy. The size was wrong, though. These blips gave off more energy than any 2 small space rocks could. Another idea was that an exoplanetary body that had not been seen before had broken down. But once more, there was no star in orbit to explain its appearance. Some physicists suggested the flashes might be the signature of Hawking radiation, the hypothetical evaporation of micro black holes. These black holes would be ancient, smaller than an atom, and near impossible to detect until they decay. If one did, it would release a sharp burst of radiation, just like what was observed. But no one's ever seen that happen before, and confirming it would require observing another one. Another possible culprit: dark matter annihilation. Certain dark matter models propose that under specific conditions, dark matter particles can collide and annihilate each other, releasing energy in the form of heat or gamma rays. But for that to occur, there has to be enough dark matter density in one location. And this dead field wasn't previously on any high-density map. Others suggested a transient event from a rogue planet, a massive object drifting through space without a star. Maybe it had a volatile atmosphere or internal geothermal activity that triggered sudden outbursts of heat. But again, WISE couldn't detect any mass large enough to support that theory. There's also the possibility of an artificial origin, not aliens, but spacecraft. Could these flashes have been the heat signatures of some distant unknown object maneuvering silently in the dark? A comet from another system firing off volatile gases? A heat leak from something we didn't launch but someone else might have? We really don't know. NASA made a list of the strange things it saw, marked the area, and planned to look at it again with the new Nancy Grace Roman Space Telescope. With its high-resolution infrared powers, that camera might finally be able to get a clearer picture of what's up there. No one can explain the flashes until then. They are just short, quiet waves in the void. Take a look at that. Something warmed up, lit up, and went away somewhere in the sky that wasn't visible to the naked eye and wasn't shown on any of our star maps. Not once, but 3 times. It wasn't noise. That was a sign. Heat-based ink with a message. Something that blinked in the dark, didn't leave a trace. No space. There is no light curve. It was only a short heat signature, but it was strong enough to make us question our ideas about where action should and shouldn't happen. The great cold spot in the cosmic microwave background. The universe gave off the faint glow we now call the cosmic microwave background, CMB, when it was only 380,000 years old, which is very young in cosmic terms. There is an afterglow from the Big Bang that covers the whole sky and has a temperature that changes by only about 1 part in 100,000. You can expect these small differences. They set the stage for later galaxies, stars, and planets. That was not the case a different part of the sky showed a huge cold spot called the Great Cold Spot, detected by the WMAP satellite, and later confirmed by ESA's Planck spacecraft. This region was significantly colder than the surrounding CMB. While typical cold areas dipped by microkelvin, fractions of a degree, this one dropped nearly 70 microkelvin below the average. That might sound small, but in the precise language of cosmic structure, It's as bold as a red X on a treasure map. At first, scientists thought it might be a statistical fluke. The universe is random after all. Given enough sky, one patch could just coincidentally be colder. But the shape of the cold spot wasn't random. It was round, smooth, and sharply defined, like a bruise in the fabric of the early universe. And its scale was jaw-dropping, spanning over 1,500 million light-years across. That's a void bigger than anything we expected to find. One early explanation was a supervoid, an enormous underdense region in the universe, where there are fewer galaxies and matter than average. The idea was that light from the CMB passing through such a void would lose energy through a process called the integrated Sachs-Wolf effect. As photons fall into a gravitational well and then climb out, they can lose some energy if the void is expanding, leaving them cooler when they arrive at our telescopes. But the problem: the observed cold spot is too deep to be explained by any known supervoid. Surveys of the area, including galaxy counts and redshift measurements, confirmed there is a void in that region, but not big enough or empty enough to account for the full temperature dip. It's like blaming a leaky faucet for flooding a house. The math just doesn't work. Some theorists turn to more exotic explanations. Could the cold spot be a sign of cosmic texture? These are theoretical defects in spacetime that may have formed in the early universe when fundamental forces split apart. Think of them like wrinkles in a tablecloth after it's been stretched too quickly. A cosmic texture would create a spherical imprint on the CMB and a temperature drop. The Great Cold Spot fits the shape and depth, making it one of the few potential signatures of this elusive physics. Others raise the possibility of quantum entanglement with another universe. In some versions of the multiverse theory, bubble universes could collide in the early inflationary epoch. If one brushed up against ours, it might leave a permanent scar like the cold spot. But this idea, while dramatic, is almost impossible to prove. The data simply isn't fine-grained enough to distinguish a universe-to-universe collision from more mundane physics. The cold spot is still one of the biggest, strange things in the universe that scientists have ever seen. Our usual view of the universe doesn't fit with this. It's too cold, too big, and too tight. No matter how much we study, we still don't know what caused it. Some experts have even said that our knowledge of gravity on very big scales may not be complete. If gravity acts differently at different lengths in space, it could change how energy moves through space and how photons from the CMB change as they travel to Earth. That is, the cold spot might not be a random spot in the sky. It could be a sign that our whole view of the world needs to be changed. Instruments like the Simons Observatory and future CMB-S4 telescopes will provide much sharper maps of the microwave background. These may finally reveal whether the cold spot is truly unique or just the most dramatic example of a broader misunderstood phenomenon. In the meantime, the Great Cold Spot remains chilling in both real and figurative ways. It's a look into the past, an old drop in the first light of the universe that no one can explain. Astronomers have been interested in and frustrated by it for 20 years. Not sure if it's a cosmic mark, a flaw in spacetime, or a ripple from beyond. A perfect circle of galaxies, with no known cause. You would expect order in deep space, but it's a mess. Huge amounts of gravity chaos over billions of years have caused galaxies to group together in filaments, spin in clusters, and spread out across empty spaces. Wildlife isn't always neat. In 2021, when scientists using data from the Sloan Digital Sky Survey said they had found a perfect ring of galaxies covering more than 1.3 billion light-years, it stopped everyone in their tracks. The structure is called the Giant Arc, and it's unlike anything else we've seen. Imagine a faint sweeping crescent of galaxies and galaxy clusters, each separated by millions of light-years. yet forming a near-perfect curve. This wasn't just a fluke of projection or a chance alignment. Multiple independent analyses confirmed its arc-like geometry. The issue is that this shouldn't exist in our current understanding of cosmology, especially in light of the cosmological principle, which says that the universe should generally look the same in all directions at big scales. One of the most important ideas in modern astronomy is the cosmological principle. It assumes that matter in the universe is spread out evenly on a large enough size. There shouldn't be a side with more organization than the other. But the giant arc doesn't follow this. It's way too big, too planned out. The arc itself measures about 1/5 of the observable universe across. That's not small. That's enormous. Its curvature suggests it's not simply a linear alignment, but a true arc in three-dimensional space. And every galaxy and cluster within it appears to share a common redshift, indicating they're all at roughly the same distance from us, and likely formed at around the same time. So, how could something so big and well-organized come into being in a world where everything is random? One idea is that it's just a random accident, an event with a very low chance of happening, but not impossible in a world with no end. But computer models of how the universe evolved don't make shapes like the giant arc. Not if you use normal physics. Not until the starting conditions are changed in ways that break other parts of the model. Another suggestion is that this could be a topological feature, a result of the way space itself is shaped. If space-time curves or loops at extreme scales, it might produce mirrored or repeating patterns. But again, this would imply a radical departure from what current data supports. Some astronomers proposed a link to primordial gravitational waves, ripples from the early universe that could have seeded unusually shaped structures. But the pattern would need to be incredibly specific, and we've never observed anything else like it elsewhere in the sky. Then there's the even stranger possibility that we're seeing the edge of something. Not the universe itself, but the boundary of a different causal domain. A region of space that evolved slightly differently due to quantum fluctuations after inflation. In such a case, the giant arc might not be a structure in our universe, but a pattern caused by a gradient or shift in physical laws from one region to another. Still, there's no proof that the physics in this area are different. No strange action from particles. There are no gravity oddities, only the arc. Another time this kind of building has caused trouble is not long ago. Astronomers had already found the Hercules Corona Borealis Great Wall many years before. It is another huge group of galaxies that spans more than 10 billion light-years. That also put the cosmological principle to the test. The giant arc, on the other hand, feels different, better, smoother in terms of geometry. It looks less like a cosmic wall and more like a line drawn on the sky. Could it be the result of a gravitational lensing illusion? That would require a foreground mass large enough to bend space in just the right way. Not impossible, but highly unlikely at this scale. And again, no such lens has been found in that region. In the end, the giant arc remains one of the best examples of observational astronomy challenging theoretical cosmology. It's there, it's real. And it's weird. Researchers are now focusing new instruments, including radio and X-ray telescopes, on the arc to gather more data about the galaxies involved. Are they interacting? Are their ages synchronized? Do they share star formation rates or chemical composition? Because if they do, it's even more mysterious. Not just that they're grouped in an arc, but also that they were all born as part of the same big planet. One thing is for sure, the world is still full of shocks. It could be a trick of the eye, a flaw in the model, or the way physics works that we don't fully understand yet. This kind of surprise can take the form of a perfect cosmic curve, the accelerating expansion that shouldn't be possible. Beginning in the late 1990s, Two groups of scientists set out to find out how fast the universe was rising. They thought that gravity would have slowed the spread that started with the Big Bang over time. Instead, they found something so shocking that it changed the way we think about the world today. It's not just growing, it's speeding up. It's not that galaxies are sliding farther apart. They're actually moving farther apart, faster and faster. The findings came from studying type Ia supernovae, a specific kind of exploding star that always reaches the same peak brightness. These supernovae act like cosmic mile markers, standard candles that let scientists measure vast distances. But when they looked out at supernovae billions of light years away, they were dimmer than they should have been. That meant they were farther away than expected. And the only explanation was that space itself had expanded more than anticipated, pushed outward by a mysterious force. This force was dubbed dark energy, a term that's basically a placeholder for we have no idea what this is. The equations of general relativity don't naturally predict accelerated expansion. In fact, when Einstein first developed them, he added a term called the cosmological constant to keep the universe static, because that's what everyone believed at the time. He later called it his greatest blunder, but now that same constant, or something like it, might be responsible for this runaway expansion. Scientists tried to calculate how much energy would be required to push the universe apart like this. Using quantum field theory, they came up with a number. Unfortunately, that number was 120 orders of magnitude too large. Not slightly off, absurdly, catastrophically wrong. That's like predicting Mount Everest will be 1,000 light years tall tomorrow. It's the most inaccurate prediction in the history of physics. One idea is that dark energy is a property of space itself. Every cubic centimeter of space, even the empty vacuum between galaxies, holds a tiny amount of energy. And as space expands, more of it is created, bringing more dark energy with it. The more space there is, the faster it expands. It's a runaway loop with no known end. Recent measurements using different methods, such as studying the cosmic microwave background with the Planck satellite and measuring local galaxy motion with the Hubble Space Telescope, have produced different values for the universe's expansion rate, known as the Hubble constant. The Planck results point to a growth rate that is slower. Hubble says it's going faster. The numbers are not coming together. They are moving apart. We have a problem with that. This difference is now called the Hubble strain, and it's making scientists think that our whole model of the universe might need to be changed. Dark energy might not always be there. It could change over time. We might be missing a piece of the puzzle, like an unknown particle, a new force, or even a mistake in how we think about gravity. Another theory proposes quintessence, a dynamic form of dark energy that changes in strength over time, unlike the fixed cosmological constant. But so far, there's no direct evidence for it. Others suggest the expansion might be anisotropic, not the same in all directions. If true, that would shatter the foundational assumption that the universe is homogeneous on large scales. We've even considered that the observed acceleration might be a mirage caused by our position in a large cosmic void. 1 second, the sky is silent. Next, it lights up with radiation, so powerful it would fry electronics from light years away. And then nothing. The most perplexing examples come from instruments like the Fermi Gamma Ray Space Telescope and Swift Observatory, which are designed to detect high-energy cosmic events. In several cases, these satellites recorded short gamma-ray bursts lasting less than 2 seconds, with no matching X-ray or optical signature and no known galaxy or celestial body at the location. One particularly strange burst, known as GRB 070201, was detected near the Andromeda Galaxy it lasted only 0.15 seconds, but released more energy than our sun will emit in its entire lifetime. Naturally, astronomers expected to find some kind of aftermath, a fading glow, a dying star, a gravitational wave signal, but nothing followed. No visible light, no radio echo, no debris. It was as if the burst came from nowhere. In one case, the burst, identified as GRB 2004-15A, lasted just 40 milliseconds. But the gamma-ray flux was so intense, it saturated instruments. The burst came from a magnetar in our galaxy, but its intensity and clean isolated signal didn't match expectations. Scientists still argue over whether it was a one-off flare or something more fundamental. There's also the scary chance that we're seeing something completely new, a type of cosmic event we don't know anything about. A black hole has a hiccup, a particle collision at very large sizes. A cosmic string snapping is a made-up artifact from the early universe that, if broken, could release huge amounts of energy. Some fringe theorists have even proposed techno-signatures, bursts of energy from alien civilizations performing astrophysical scale engineering. While that's not the mainstream view, the absence of any physical source keeps the door cracked open. A void in the universe so big it breaks the models. You expect to find empty spots in space where there aren't as many stars, galaxies, or objects. But in 2007, scientists found a place that was so empty and barren that it didn't fit any of our models of the universe. It wasn't just a space, it was the supervoid. A huge dark space in the universe that was almost 1.8 billion light-years across. Plus, we still don't understand how it works. Let's put that size into perspective. The Milky Way galaxy is about 100,000 light-years wide, so this void could fit 18,000 Milky Ways end to end, and still have room to spare. It's located in the constellation Eridanus, which is already home to another cosmic anomaly, the cold spot in the cosmic microwave background, CMB. NASA and ESA are preparing next-generation gamma-ray detectors like Amigo X and Theseus, which aim to localize these mysterious bursts more precisely. The hope is that with higher resolution and faster response times, we'll catch one of these anomalies in action and finally trace it back to its source. Until then, we wait. At first, scientists assumed these were unrelated, but the more we looked, the weirder it got. The cold spot was first detected by the Wilkinson Microwave Anisotropy Probe, WMAP, and later confirmed by the Planck satellite. It showed a region in the CMB, the afterglow of the Big Bang, that was noticeably cooler than its surroundings. This alone was strange, since the early universe should have smoothed out such temperature differences over billions of years. But when researchers pointed radio telescopes at that same spot in Eridanus, they realized something else. There were far fewer galaxies in that direction. The density of galaxies dropped by up to 20% compared to similar patches of sky, and it wasn't a local dip. This void stretches across hundreds of millions of parsecs, both wide and deep. It isn't just a gap, it's a scar, a wound in the fabric of the universe that current physics can't explain. Now, voids aren't rare. The universe is structured like a cosmic web. Galaxies cluster along filaments, with empty spaces in between. These are normal, but the Eridanus supervoid is too big, too empty, and too cold to be brushed off. According to our best simulations of cosmic evolution, such a structure shouldn't exist in the observable universe. So, what's making it happen? It's possible that this supervoid is just a statistical blip in a very big set of data. Most models, though, say that the chances of such a gap appearing naturally are less than 1 in 50,000. The integrated Sachs-Wolf effect is another idea. This effect says that photons from the CMB lose energy as they move through big holes or wells of gravity. It's possible that this could explain the cold spot, but the amount of energy lost doesn't fully match what has been seen. Others have suggested it could be a sign of non-standard inflation, meaning the early universe may have expanded in ways that vary by region, causing uneven temperature and density profiles. But this theory threatens to unravel the whole idea of cosmic homogeneity. The principle that the universe looks roughly the same everywhere on large scales. Could the gap be the mark of a bubble universe, a place where different physical rules applied that brushed up against our own universe right after the Big Bang? This idea of a cosmic bruise is debatable, but it seems to fit. You might see scars like these if our universe is part of a bigger multiverse and bubble worlds sometimes crash into each other. Radio arrays and infrared cameras are still doing new scans to figure out how big it is. And new projects like the UK IDSS Space Telescope and the Nancy Grace Roman Space Telescope may help make things clearer. The cosmic web, filaments that pulse for no reason. If scientists take a big picture look at the universe, they don't just see a bunch of galaxies here and there. Instead, they see structure, the cosmic web, a huge web of matter that is all linked to each other. These filaments are huge threads of dark matter and gas that connect galaxies and clusters, like roads on a huge map of the galaxy. They stretch over hundreds of millions of light years. The universe is held together by these threads. But lately, someone has seen something strange. Some of these huge strands don't just sit there in a straight line. They beat. Yes, pulse means to shine, change in energy, or act in slightly rhythmic ways every so often. No one understands the reason. Cool places. There are dead zones. There is proof of effect. Of course, this is still just a guess. There is no clear proof that there are other worlds. And most physicists still think of the multiverse as a theory that hasn't been proven. But when it comes to strange things like the Eridanus supervoid, people's imaginations tend to take over when facts fail. The fact that this void doesn't seem to be moving nearby galaxies in a big way adds to the puzzle. If an area this big was really less dense, it should have effects on gravity. But the galaxies around it aren't acting strangely so far. It seems like this empty space is always there. Huge, still, and uninteresting. Imagine a building hundreds of millions of light years long that slowly changes its brightness for no clear reason. Some scientists think that these pulses might be caused by shock waves, which are huge bursts of energy that happen when galaxies or dark matter collapse, but that still doesn't fully explain why the changes happen at the same time or over and over again. In some places, the gaps are too consistent, almost like the beat of a heart. But space doesn't have a heart, does it? Another theory suggests the involvement of magnetic reconnection, the same process that causes solar flares on the sun. If magnetic fields in these filaments twist and snap back into place, they could release bursts of energy. But to apply that mechanism across a structure spanning millions of light years requires a scale of magnetic influence we've never observed before. There is also the chance that dark matter is doing something we don't know about. We know that dark matter gives these strands their shape. It doesn't give off light, but it has a lot of pressure. It's possible that dark matter can engage with itself in strange ways. The discovery came from a combination of observations using radio telescopes and X-ray surveys. Astronomers noticed that certain filaments, particularly those connecting galaxy clusters, were showing time-variable emissions. That's weird enough. But it gets stranger. These emissions weren't tied to any specific event like supernovas or black hole activity. They seem to fluctuate with no local cause. One of the most studied examples is a filament connecting the AEL-222 and AEL-2223 galaxy clusters. Researchers detected a bridge of X-ray emitting gas between the two clusters. That was expected. Hot gas trapped by gravity. But over time, the brightness of this bridge subtly changed. At first, scientists thought it might be due to intervening objects or data error, but repeated measurements showed a real rhythmic variation in intensity. Ask ChatGPT. If that's the case, it could be sending out small density waves that heat up or squeeze the gas stuck in these cosmic bridges, which is what we see as pulses. But for this to work, Dark matter would have to have qualities that aren't in current models. This could mean that dark matter interacts with itself, or even that dark plasma exists. In order to understand how the universe is put together, some researchers have found even stranger links between dark energy and entropic forces, string theory fields, or even information theory. These links suggest that dark energy may be connected to the very structure of space-time, or be a result of entropy balancing itself across the universe. Despite its dominant presence, we can't detect dark energy directly. It leaves no spectral lines, no mass signature, no particle trail. Its fingerprints are only visible in the motion of galaxies and the stretching of light. That makes it not just strange, but dangerously untestable. At least with current instruments. The Nancy Grace Roman Space Telescope, which is set to launch in the next few years, will look into dark energy with a level of accuracy that has never been seen before. It will try to figure out how we change over time in space by making maps of billions of galaxies and supernovae. And maybe, just maybe, it will tell us if the force speeding up the universe is a quiet whisper or a rising scream. A rogue planet with no star emitting radio signals. We usually think of planets as loyal partners to stars, stuck in circles and held together by gravity and light. But some worlds don't follow the rules. Some people wander around by themselves. Rogue planets are big, cold worlds that are floating through space without a star. Another one was found in 2016 that did something that no one thought a rogue planet would do. Radio waves came from it. The object, known as SIMP J0136566 3all9334373, or just SIMP for short, is a planetary mass body located about 20 light-years from Earth. It was discovered as part of a survey looking for failed stars called brown dwarfs. Objects too large to be planets, but too small to sustain fusion. But SIMP defied categorization. It was originally classified as a brown dwarf. Then, with more refined data, scientists realized it was only about 12.7 times the mass of Jupiter, right at the boundary between a planet and a star. Using the Very Large Array (VLA) in New Mexico, researchers detected strong radio emissions coming from SIMP emissions that resembled the auroras we see on planets like Jupiter, but much more powerful. We're talking about radio bursts in the gigahertz range, far stronger than any planet is supposed to be able to produce, without a host star's energy driving its magnetosphere. A cold, starless world that is floating through space and giving off radio waves. There is only electricity and wonder, no sun or moon. So what's making it happen? SIMP has a magnetic field that is over 200 times bigger than Jupiter's. This is the most likely answer. If the planet has a moon or ring system that interacts with the field, that is enough to make the aurora happen on a big scale. Some scientists think that SIMP's strong radio bursts could be caused by a huge exomoon circling and setting off magnetic interactions in the same way that Jupiter's moon Io causes its auroras. It's just that we haven't seen such a moon yet. There is no sign of one in the visible or infrared spectrum, but the radio flashes keep coming. It seems like SIMP is running on its own power. Some scientists think that rogue planets like SIMP may still have heat inside them from when they were formed, which could keep oceans or hot cores alive for billions of years. That heat, along with metallic hydrogen deep inside, could make a strong planetary dynamo. This would be like how Earth's iron core makes its magnetic field, but on a much larger scale. This might explain the magnetic power of SIMP, but not the fact that its signs come at regular times. What's really strange about SIMP is that its radio output changes over time and rotates like a pulsar. It's like the Earth has a radio energy beam that goes across the sky like a lantern. That's not how planets usually work. It's how neutron stars and other strange leftovers work. This led to thoughts on the edge. Some experts have thought that SIMP might not even be a planet, but a new type of object called a planetary mass radio emitter, whose power source is still unknown. Could it be reacting with the space between the stars in a strange way? Could its magnetic field be hitting charged particles in space, which would keep the aurora going in a way we've never seen before? Then there's the wildest theory. What if some rogue planets carry remnant stellar cores left over from failed binary systems? Or possess dark matter interactions that somehow contribute to sustained energy output? No solid evidence supports this, but the fact that SIMP doesn't fit our neat little boxes leaves the door cracked open. Since the discovery of SIMP's emissions, astronomers have started pointing their radio arrays at other rogue objects. A handful now appear to show similar, if weaker, radio traits. This raises the possibility that radio-loud rogue planets are more common than we thought, and we've simply been blind to them until now. If rogue planets can emit detectable radio waves, they could be accidentally masquerading as other celestial sources in deep space scans. That mystery blip in a survey, it might not be a distant galaxy or a supernova remnant. It might be a planet quietly howling as it drifts between the stars. More practically, this opens a new method for detecting free-floating planets. Traditionally, we find them via gravitational microlensing, a difficult and rare event. But if we can start identifying rogue planets by their radio signatures, it could vastly expand our knowledge of planetary systems beyond stars. X-ray jets from the middle of nowhere. There are many jets in the universe. We see them coming out of black holes, new stars and galaxies that are powered by giant engines. These jets, which are usually made up of very high-energy particles, shoot out in orderly columns and move at almost the speed of light over unimaginable distances. X-rays, gamma rays, and radio waves can make them light up. However, every known plane has a source. One exception. Astronomers found a single X-ray jet in a part of deep space. A beam of high-energy radiation that seems to appear out of nowhere and is about 1 million light-years long. NASA's Chandra X-ray Observatory was the first to see this event. This is a satellite that is meant to find some of the most energetic and faraway things in the universe. The jet was weak but clear. It pointed in a single direction like a cosmic arrow, and its shape was strangely clear. It acted like a normal AGN jet, but you couldn't see what its source was. That's like seeing a smoke path, but no fire. There is no chimney, not a building. It's just smoke floating in the air with no source. Astronomers, of course, rushed to figure out what was going on. Some people thought the jet might have come from a quasar or black hole that has since changed its brightness or moved out of view. But even if the source went away, we should still be able to see signs of it, like a faint galaxy, an infrared signal or gravity structure that is still there. There is only cosmic emptiness instead. Another theory. The black hole that launched the jet might have been ejected from its host galaxy due to a gravitational interaction, such as a black hole merger recoil, where two massive black holes combine and kick the final product out of the galactic core. If true, the black hole could now be flying solo through space, dragging its ancient jet like a flag behind it. But there's another catch. The black hole is also gone. Not many big groups. There is no radiation. There was no change in the light in the background, only the beam. The universe shot an arrow and then raced the shooter. This discovery has baffled scientists because the jet's properties match those from known sources. The structure suggests it is powered by relativistic particles accelerated along a magnetic field. Textbook black hole physics. Yet the very existence of this jet violates that textbook by lacking the engine. Some people think the jet isn't coming from a black hole at all, but from an unknown type of cosmic engine that doesn't give off light or gravity pull. In the usual ways, this might be a dark matter object, but not a clump. It might be something moving that only gives off radiation in strange situations. Or is the jet something that is left over, like an artifact from before galaxies? To test these ideas, scientists turned to multi-wavelength surveys, hoping to catch any supporting clues in infrared, optical, or radio frequencies. Nothing turned up. The jet remains a ghost, detectable only in X-rays. The building itself is strange. There is no turbulence, knots, or flare in this jet like there is in other jets. It has been in space for millions or even hundreds of millions of years and has kept its shape. That means the starting point has a lot of energy and is very steady no matter where it is. Some researchers tried to use gravitational lensing models to account for the odd location. Maybe the jet appears displaced because of warped spacetime from a massive object in the foreground. But this too fell apart. Lensing would have bent the jet's light, but not eliminated the source. The problem isn't distortion, it's absence. There were people who really believed that the jet could have been an echo, like a light trail from something that fell into a higher dimension or went through a wormhole. It's only a guess, these ideas, since there's no real evidence to back them up. Jets are thought to be caused by giant processes, but this one doesn't have any mass nearby. This could mean that we're missing a whole class of unseen cosmic engines. Or we don't fully understand it yet. The galaxy that appears to have no dark matter. Dark matter holds the world together, but we can't see it. It doesn't give off light or radiation, and electromagnetic forces can't affect normal matter. But galaxies shouldn't exist without it. Models and simulations that have been running for decades say that the gravity of stars, gas, and dust isn't enough to keep galaxies together. As they spin, they should fly apart. Dark matter's extra mass holds everything together, even though it can't be seen. Every galaxy we know of needs it. One exception. Astronomers using the Dragonfly telephoto array reported in 2018 that they had found a galaxy called NGC 1052 DF2. It is made up of a faint, spread-out group of stars that are floating about 65 million light-years away. From far away, it didn't look like anything special. But when scientists looked at how it moved, they saw something amazing. There wasn't enough speed in the stars. There was no dark matter at all. So the galaxy's internal speeds were exactly what you'd expect. That's surely not enough. That's nothing. The implications were immediate and massive. If NGC 1052 DF2 truly lacks dark matter, it overturns a major assumption that dark matter is essential for galaxy formation. It also suggests that galaxies can somehow form and stay stable using only their ordinary matter. Normally, astronomers measure a galaxy's mass by observing how fast stars orbit the center. The faster they orbit, the more unseen mass must be pulling them in.